All right, so as I get the recording going. So last time I ended up not covering everything because I had an unplanned digression that ended up going on for 30 minutes. Whoops. So I'm going to finish that up today, and then I have only a little material, relatively little material for the next section, but I also have another digression this time planned, and I'm going to save it for the end. Actually, that's the only place where it makes sense. And if I don't get to it, well, I'll just disrupt some other class period with it. No, I'm not going to go so far as to talk about numerical linear algebra during PDE. Don't worry about that. But, well, you never know, actually. So, let's see. Notes. Okay, so picking up where I left off with the singular value decomposition, and there's quite a few applications of the SVD, but what I want to focus on today is one in particular, low rank approximations of a matrix. So to bring back something I covered last time, okay. The SVD expansion. So if A is equal to U sigma V transpose, then this is saying exactly the same thing as that, because this is another way of writing a matrix product where UI and VI are columns of U and V, and sigma I, these are singular values. These are the diagonal entries of sigma. Now, normally this sum would go from 1 up to the minimum of m and n, where A is an m by n matrix. But R, which is a rank of A, is also the number of non-zero singular values. So, and remember, singular values are always ordered from largest to smallest. So sigma 1 being the largest. So you really only need R terms, and that will give you A exactly. Okay. All right. So what you can do is, what if you decide to truncate this series, this sum? So here we have a same sum, but I'm cutting it off after k terms, where k is strictly less than a rank. So I'm tossing out certain terms that correspond to the smallest singular values. So this right here is referred to as the best approximation of A by a matrix that's of rank k. So the number of terms in this sum is the rank of whatever matrix you have here. So A is approximated by this matrix of rank k. Now it turns out we actually have a clear idea as to what the error in this approximation is. So if I want to look at all matrices B that have rank k, and I want to make this error, so the deviation between a rank k matrix and A, I want to make this deviation as small as possible. Well, to make this as small as possible, I would choose B equal to this matrix right here. So this is why it's the best approximation, because it minimizes this error in the 2 norm. Now, if A has all R terms and AK has the first K terms, then the error would just be the terms that are left, the terms that got tossed out. So I going from K plus 1 up to R. So this is a matrix of rank R minus K, and these are the singular values. So the largest singular value is the one with the smallest index, k plus 1. So sigma k plus 1 is the error in this approximation. And that just comes from what I mentioned last time. The 2 norm of a matrix is the largest singular value. Well, sigma k plus 1 is the largest singular value of the error. So, so in other words, this is a measure of how closely you can approximate A with a matrix of rank k, sigma k. So it's the next singular value. There's one additional statement I can make about AK. It's not just the best approximation to 2 norm, but also the Frobenius norm. And I can tell you what the error is in that case too. So A minus AK. Frobenius norm is also related to the singular values. So if you take all the singular values starting from k plus 1 all the way up to sigma r, which is the smallest non-zero singular value. So you take the sum of square root of sum of squares of those, and that's the error in the Frobenius norm. And that comes from the fact that the Frobenius norm of a matrix is the sum of square root of sum of squares of all the singular values. All right. So how we can interpret this error that whatever the smallest singular value you have is, that's the distance between A and rank deficient matrices. So now if A is already a rank deficient, like if it's a singular matrix, then that distance is 0 because it's a distance between A and singular matrices. It's already singular. Okay. So this singular value gives you an idea of how close A is to a matrix of rank K. So in other words, there's a matrix of this size in the 2 norm that you could add to A that makes it have lower rank, or sorry, rank K. All right. Now, one thing that this tells us is if a matrix A is full rank, that means all the singular values are non-zero, but they can still be arbitrarily small. So that tells us that if you take sort of all full rank matrices, and so apologies to anyone who's traumatized or triggered by the real analysis talk, but so the set of all full rank matrices is open and dense. So what that means is if you have any full rank matrix, there's another full rank matrix that's arbitrarily close to it. Or like even say if A is a singular matrix, it's still arbitrarily close to a full rank matrix. In other words, you tweak it just a tiny little bit and it becomes full rank. So there's another way of saying that, in fact, essentially most matrices are full rank. Just that there's certain matrices within that set that are singular. Okay. Now, I want to point out, what do we get from a low rank approximation? How does that help us? data compression. So suppose AK is a good approximation of A. Then the storage needed for A, if you just store A in a regular way, is M times N, just a regular two-dimensional array. But instead what you can do is you can store the SVD of AK. Now, how much storage do you need for that? Well, you need K left singular vectors that have length M. We need K right singular vectors of length N. And you also have to store K singular values, which are just numbers. So the total storage is M plus N plus 1 times K. So suppose K is much smaller than both M and N. Then you're saving a lot of storage. And for certain types of matrices, you probably get away with an approximation that is extremely low rank. So you can still represent A fairly accurately. So this is especially useful for images. Okay. All right. Which reminds me, I want to see if I can somehow illustrate this. And I know I'm bad about doing these digressions, but still, if it highlights some applications, certainly that can only be a good thing. Okay. But I need something good to try it on. And I don't have a great selection of pictures. On this laptop. Okay. Oh, all right. I think I have something I can work with. All right. Okay. I'm going to take a few minutes to try something here in MATLAB, and hopefully it goes well. Okay, so unshare and reshare. Okay. So let's give us a shot here. So what I'm doing here, I should start a diary. Okay. Now I have an image file, and image read will read this image into A, and A, well, that's not what I wanted. Whoops. Okay. Let me just repeat that. Okay. You know what? Sorry. I don't want that junk in the diary. I don't want to have to edit it later. So I'm going to delete the diary. Start it again. Okay. All right. So now I want to show you the size of A. 1000 by 1194 is the dimensions of the image in pixels. The 3 is because this is a color image. So we have channels for RGB colors. And the type of data you saw it flash on the screen is all these integers from 0 to 255. So 0 for black and 255 for full color. Now I'm going to take just one of these channels. I'll take the red channel. So that way I'm working with a matrix. And so now if I do, and I need to convert it to double because these are unsigned 1-byte integers. And I want double precision floating point numbers, what I'm about to do. So I'm going to convert it to double. Now, if I try, okay, if I try surf of A1, okay, that doesn't really show us anything. But then if I do shading flat, okay, and then I'll do view 0, 90 to look down on it from above. Right there. Oh, whoops, it's upside down. But it's a cat. So, okay, I'm going to try 0 minus 90. There. Okay, we have a cat. So now, and this is just from a red channel, but all the other channels would look fairly similar. And that's what we see generally for color images. Now, this is a matrix of size 1000 by 1194, so there are 1000 singular values. I'm going to plot the singular values. Okay, so I need the SVD. And I'm going to plot S. Okay. Actually, you can't really tell very well, but the singular values tail off very sharply. I'm going to plot it again on a log scale. Values semi-log y. All right. I want figure 2. Oh, I goofed here. S is a diagonal matrix. I actually want the diagonal of S. Okay. Okay. Yeah, here it's still, again, it tails off rapidly. So now I'm going to do log of a diagonal. Okay. Okay. Here, it starts out the largest around 10 to the 6. Then very quickly, it's down to 10 to the 0. And then there's practically nothing after that. Now, we still have a lot of non-zero singular values. But what I'm wondering is, since it tailed off so quickly, like several orders of magnitude, what if I cut it off after, let's say, just 100 singular values? So the way I'll do that is... All right, so A100 will be, I'll take the first 100 columns of U times the first 100 by 100 block of S times the first 100 columns of V, but that's transposed. So that is a rank 100 approximation of this 1000 by 1000 matrix. So now I want to show that and see what kind of approximation it gives, or at least visually. Okay. Oh, that didn't go so well.
I was going to say, shouldn't that be 1 colon 100?
Oh,
100.
Yes, it should be. Yep. Okay. Thank you for catching that. Yeah, it's, I want columns 1 through 100 of U and V. Okay.
I think same for the S, right?
Oh, yep. Okay. This is what happens when my digressions are unplanned. Okay. Okay. All right. Well, at least it's recognizable as a cat. At rank only 100. Certainly certain colors are thrown off, and you can kind of tell there's not quite as much detail. Actually, I do have a color bar here on both. The scales are a little different because of a. So that's why like these reds are different. But if I force these to be equal, then these probably would look much more similar. What if I got more ambitious and tried rank 50? I'll try actually doing it right this time. Dang it. Okay. Okay. It's getting blurrier. It's starting to lose quite a bit of detail. So maybe rank 50 isn't such a good idea. Rank 100 wasn't bad though, and that's just taking 10% of the possible singular vectors and singular values. So, and so with images in general, you get something that's fairly recognizable as the original image by even with quite a bit of compression. So that's something to keep in mind. So any questions about what happened here in MATLAB? So I'll post this diary later after removing the wrong statements. Okay. All right, so that's what I want to say about the singular value decomposition. Oh, actually, okay. A quick example of low rank approximation. Okay, so first I need to recall an example from last time. Okay, so here's a matrix of 3 by 3, and I presented the SVD last time. We see that there are only 2 non-zero singular values. This is rank 2. So that's the SVD expansion. So now, if I want an approximation of A of rank 1, that just means only taking this term. Okay, whoops. I have to show the rest of the matrix. Okay, so this singular value times U1 V1 transpose, this is U1, first column of U, and this is the first column of V transposed. You work all this out, simplify what you can, and this is a matrix that you get. Now, if we compare this matrix of rank 1, we see it's rank 1 because all of the rows and columns are scalar multiples of each other, or actually they're equal, all the rows are equal. To the original matrix, 10, 20, 10 is the approximation. You see it's not very far off. So now, if I look at the absolute error, that's just a singular value that got tossed, so the 2.4495. Now I want relative error. If I divide this by the norm of A, which is the largest singular value, then this is what I get. So this is a good measure of error, relative error, in the low rank 1 approximation. So it's a little less than 6%. Okay. So, and the reason why it's pretty accurate is look at the size disparity in singular values. The first one is much larger than the second. So when you're tossing out terms whose singular values are much smaller than the ones you're keeping, that's an accurate low rank approximation. Whereas if these had been about the same magnitude, then this error would have been a lot higher. Is there any questions about low rank approximations? I have one more least squares topic to cover, and then we were getting out of this chapter. Now, we've only looked at okay. Actually, there's one section in this chapter that I skipped. It's section 4.3. If I want to talk about the SVD, if A is not full rank, then we can find a minimum norm least square solution. So if AX equals B has infinitely many solutions, we can pick a unique one by making the norm of X as small as possible. Whereas if A has full column rank, there's a unique solution to this. And that's from using normal equations or the QR factorization. So now I want to try a variation on this problem for full rank least squares. It's a least squares with linear constraints. Okay. Now, least squares problem is good for fitting data. Like if you have certain points in the plane and you want to match them with certain functions, like polynomials, for example, you can use a least squares problem for that data fitting problem. Like a simplest case, finding the line that best fits some data. So you take a linear combination of a constant function and a linear function to do that. But what if you're trying to use different functions to fit the data on different subintervals? So maybe you want to use a linear in one case, a quadratic in another part of a domain. And one example that comes up in numerical analysis classes, some of you saw this last semester, fitting data using cubic splines, a different cubic spline for each subinterval. So what happens in that case is there are certain constraints that have to be satisfied, like using a different cubic polynomial on each subinterval, but they have to be continuous, they have continuous derivatives. So that imposes constraints on the coefficients. And because you want something that has is a smooth curve, but also fits the data well. Okay. Okay. So requirements like continuity or having continuous derivatives lead to constraints on your coefficients. So what you get is least squares problem with linear constraints. So how do we solve such a problem? So in other words, we're trying to minimize b minus ax like before, but now we have additional conditions to consider. So now I'll state the general problem. In matrix form. So we're given A and B like before, and you still want to minimize b minus ax, just like in the full rank least squares problem. But now you're given this matrix C, it's n by p, whereas A is n by n, and D is a p vector. And your solution X to this problem also has to satisfy C transpose X equals D. So this system of linear equations describes your constraints on X. And if this is your objective function, this is what you're trying to minimize. Now, how can we solve this? Well, there's an approach that you actually learn about in multivariable calculus, Lagrange multipliers. So that's what I'm going to apply in this case. So how that method works is you define a function of x. See, this should be a bold x. Okay. Great. Another typo in a book. Can't have a class without one. Okay. Sorry, I have to make a note of this because most definitely will forget. Okay. All right. Now, so let me get the rest of this equation here. So we define this function f depends on x and also these Lagrange multipliers, which are a vector lambda. So we're trying to minimize this, but we also take this into account. A factor of 2 is going to be for convenience later. So solving this constrained minimization problem is equivalent to solving the unconstrained minimization problem of finding where this has a minimum. So what you do is you take the gradient. Okay. I should say this is the gradient with respect to x, the x variables. Or if one you can think of as a function of x where lambda happens to be a parameter. Now, we can also take the gradients in the lambda variables. So if we take a partial derivatives of f with respect to f with respect to the lambdas, you get nothing from here, and then here you're going to get 2 times c transpose x minus d. D, not x. Okay. Now, to find a minimum of this function, we need the gradient to be 0. All of this should be 0. That should be 0, and that should be 0. Well, but making this 0 means the constraints are satisfied, so now you don't have to worry about them anymore. And now we have this part to handle. So another way of looking at it is I can describe this if I consider what's multiplying x and lambda. If you were to multiply this out, I get A transpose A x plus C lambda equals A transpose B, which is what you get from setting this equal to 0. And then here I have C transpose X plus 0 is equal to D. So in other words, coming from setting this equal to 0. So solving this system for x and lambda is equivalent to solving both of these equal to 0. That's what we need to find a minimum. Now, from setting this equal to 0, what I can do is I can multiply both sides of this by A transpose A inverse, which is known to exist because A has full column rank. Now, what's interesting about this is if we keep in mind the regular unconstrained least squares problem, that the solution of the unconstrained problem satisfies the normal equations. So if I multiply both sides of this by A transpose A inverse, then x hat, which is a solution of the unconstrained problem, satisfies this. Now, why is that helpful? Because this is the first term up here. So, in other words, I can write the solution of my constrained problem, which is x, as a solution of the unconstrained problem, x hat, and then I have this additional term here. So that's really my first step in solving this problem. Solve the least squares problem without the constraint, and that's just by solving the normal equations or using a QR factorization. But now, how do I get this lambda? I still need that to be able to express my solution x completely. So here's how I'm going to do that. I'm going to take this equation and multiply both sides by C transpose. But now I take into account my constraint. I know what C transpose X is. It's equal to D. So even though I don't know what X is yet, I do know what this is. So now I take that into account. So now I set this becomes D. So now I have this equation that I can now solve for lambda, because at this point, everything here is known except for lambda. But now I can solve this. And then once I have that, I can take lambda that I solve for and use it up here. And now I have my so now I have my solution. So my solution formula is this. This I get from the unconstrained least squares problem. This part I take care of by solving this equation for lambda. Are any questions up to this point? So we have the equations to solve like on paper, but how would a practical algorithm proceed? Well, first I need to solve the unconstrained least squares problem. Now you could use normal equations, but I'm going to use a QR factorization. And it's the economy size QR factorization. So A is m by n, Q is also m by n, and R is the n by n non-singular upper triangular matrix. Now I solve the unconstrained least squares problem by solving this upper triangular system by back substitution. So now I have my x hat. Now, if I take QR and substitute it for A in here, I'm going to get Q transpose Q in the middle of this, but that's identity because Q has orthonormal columns. So A transpose A is the same as R transpose R. So my equation for lambda is now written like this. Now you might think, well, how does that help? All I did was change A transpose A to R transpose R. It actually makes a huge difference. And the reason why is A is m by n. Think of it as a tall, thin matrix. R is a square matrix. What that lets me do is something I could not do up here. I can take the inverse of a product. Because remember, the inverse of a product is the product of the inverses in reverse order. So R transpose R inverse is equal to this. So because R is square, R transpose R and R are invertible individually, whereas A is not square. I could not talk about the inverse of A or the inverse of A transpose. That's what the QR factorization buys me. So now, if I take this and substitute that in here, now I have the equation in this form, where W is R inverse transpose times C. Now, and what that means is to get W, solve R transpose W is equal to C. And remember, R is upper triangular. So what I could do is I could solve this system by forward substitution, because R is upper triangular, therefore R transpose is lower triangular. And I can apply that with each column of C, and that'll give me each column of W. Dang it. So once I have W, now W is not a square matrix generally. So now I compute its QR factorization. So U will be a square matrix, upper triangular, non-singular. So W transpose W is the same as U transpose U. So now my system for lambda is in this form. And U is upper triangular. So I can use forward and back substitution. So I solve U transpose Y is equal to the right-hand side, C transpose X hat minus D. And then I solve U lambda is Y. So it's kind of like with LU factorization, it's the same idea that I call this Y, solve this system for it, and then U lambda equals Y. So now I have lambda. Almost there. So now here's my solution formula. And I can plug lambda in, but notice if I replace A transpose A again, I have this. And R inverse transpose C, this part right here, I already have it. It's W. So I can fill that in. So I can compute W lambda, that's a vector, and then solve this system to get this expression right here. And now I'm done. And I have my constrained least square solution. So what you can see is, even after you have a formula worked out, this formula right here for X, and which also relies on this formula for lambda, you don't want to just code this up and solve it. Like, you don't want to actually compute A transpose A in MATLAB and then like compute its inverse, because one of the things you're seeing in the homework is A transpose A can be very ill-conditioned. That's why we do all this instead, using QR factorization. So you don't want to solve a system involving a matrix transpose times itself just as is. Use something like this, like a QR or also a Cholesky decomposition, and that leads to a more numerically stable way of solving. And this is the disconnect between like theoretical and numerical linear algebra classes. That a theoretical linear algebra class would probably stop here. It's like, oh, here's the answer. It's like the joke about the engineer, physicist, and mathematician who stay at a hotel. The engineer wakes up in the middle of the night and smells smoke, goes out in the hallway, sees a trash can on fire, sees a fire extinguisher, uses it, puts out the fire, and goes back to bed. Physicist, encounters the same situation later that night, finds the right angle at which to point the fire extinguisher to put the fire out with minimal foam used, and then goes back to bed. And then finally, the mathematician goes out the hall and sees the trash can on fire, sees the fire extinguisher, and says, aha, a solution exists, and goes back to bed. I'll assume you're all laughing behind your mutes. Okay. Okay. Or groaning, probably groaning. Okay. So the formal algorithm is here. Okay, so this just describes the steps that I was just deriving. But I didn't want to just show this algorithm like, like, oh, how does this relate to the formulas up above? Well, here's how. Okay. The one and only homework problem from this section is to implement this. Okay. Now, I want to point out what's flawed with it, though. And it does work, but it's not the best approach. Because by including Lagrange multipliers, you're taking this problem involving ax equals b, and you're adding variables to it. If you're imposing constraints on a system ax equals b, then you would think that should lead to a problem with fewer variables, not more. So there's a certain amount of expense added, depending on how much, depending on a number of constraints. So it just seems a little bit counterintuitive that you're taking away degrees of freedom, therefore taking away a number of unknowns, and yet you're doing more work. Now, there is another approach that I did not assign homework on, and I will include it in the notes. I just won't take the time to discuss it here, just because I don't think I would be able to in time. But what it does is it actually relies on a QR factorization of C rather than R. And it uses that to solve a problem with fewer variables instead of one with more variables. But a problem with that approach is if the original least squares problem, linear constraints, involves sparse matrices, then this approach might destroy sparsity. So no one approach is has all the advantages. It just depends on the particulars of your problem. And if you have maybe only a very few constraints compared to the size of X, maybe Lagrange multipliers is perfectly fine. What I would rather do is, again, I mentioned I had another digression planned. We've been talking all chapter long about overdetermined systems of equations. So if your matrix A is m by n, m greater than n, full column rank, then we know that this system Ax equals b might not have any solution. And we know how to find a minimum. So by solving the normal equations, and that gives us this solution formula: X is equal to A transpose A inverse A transpose B. So now I want to talk about the opposite situation. Let's suppose that M is strictly less than N. So the system is underdetermined. And we'll assume that A has full row rank. So that'd be rank M. Okay. So then Ax equals B has infinitely many solutions. Now, what solution formula do we have? Do we have a solution formula that's like this one? Now, we do have one that I covered last time, involving the pseudo-inverse. But that's very expensive to compute. But it turns out there actually is a solution formula for the underdetermined case that's similar to this one for the overdetermined case. And I actually use what I've just been talking to you about. As a least squares problem with a linear constraints. Okay. Oh, whoops. Okay. All right. Now, so how this can be done, and I actually have a couple approaches in mind, but okay. We want to minimize. So I want the minimum norm least squares solution, and okay. So I'll make clear what I'm finding a solution formula of. Minimum norm solution. So a solution that satisfies AX equals B, but also has minimum norm. So I want to minimize the 2 norm of X subject to AX equals B. So that's the same as a least squares of linear constraints problem with these notation changes. So B, from the original description of a general description of a problem, becomes 0. A in that problem becomes minus identity. C becomes A transpose. And D, the vector D, becomes B. In other words, since I have a way of solving this problem, I can just go ahead and use that solution formula where I make these notation changes. So from a general solution formula, what I have is X is equal to X hat minus C A transpose A inverse. Actually, I need to check this. Okay. Oh, C transpose, not C. Okay, that should be C transpose. C lambda, where lambda satisfies this system of equations. Wait, so I need to check the rest of this. Oh, sorry, I goofed. Okay. This equals, okay. So I have everything fixed up in a jiffy. Okay. Okay. All right. So I need to use these solution formulas and just make all the appropriate substitutions. All right. Now, oh, I should mention X hat. That's A transpose A inverse B. Okay. Now, B, however, becomes 0. So X hat is 0. All right. What about lambda? Well, A is minus identity. So all of this in here becomes identity. And then C becomes A transpose. So therefore C transpose is A. So I have, so this becomes A transpose lambda. Is equal to C transpose X hat, but that's 0. And then D is B, so that's going to be minus B okay. And over here I have, okay, X hat is 0, so X is equal to, well, that's just going to be identity. And then C lambda, so that's going to be A transpose, or sorry, minus A transpose lambda. Okay. So now what I can do is solve this equation for lambda, and then put that expression for lambda in here, and so I get X is equal to A transpose, A transpose inverse B. Okay. So if I were to multiply both sides on the left by A, I'd have AX, and then I have AA transpose, then AA transpose inverse, they cancel out, and you get B. So this does satisfy X equals B. And based on this is meant to minimize this norm here. This is a minimum norm least square solution. Now, it's gone off the screen. Compared to the overdetermined case, we have solution of that least squares problem is equal to A transpose A inverse A transpose B. So you can see the similarities and differences between the two. We're taking A and A transpose in some combination, inverting them to opposite ones in each case. In the overdetermined case, this is a square invertible matrix, whereas in the undetermined case, this is. And then if A transpose on different sides, depending on which problem it is, all multiplied by B. So I want to show you how we can come up with a formula like this fairly quickly just by recognizing what kind of problem this is. It's a least squares linear constraints problem. So I would just go ahead and use this solution formula and apply it to this case. And this is what pops out. Another way to solve it, which would take a bit longer, is if you try to solve this using a Lagrange multipliers directly, like you form that function f, and you take its gradient and try to make it 0, then that would be another way to arrive at this formula. Okay. So any questions about what happened here? Or any homework questions?
I have like a futuristic question, if that's okay. At least with when I get to this. So this very last problem we work for the homework, the algorithm that we're coding, I'm assuming we can, there's probably like MATLAB functions that implement some of these things, like built into it, or is it something we have to like build up?
Wait, which problem exactly?
Just, can you go, you said it was the only problem we'll do in the section and earlier, if you scroll up in the note.
Implementing this algorithm?
Yeah, are there like, you know how sometimes MATLAB will have certain built-in functions with it, like you can, I don't know.
Well, for this is something I discussed it was a few classes ago. MATLAB has a QR function.
Right.
And there's a way to call it. If you look at the section on notes on Graham Schmidt, how to get the economy size QR factorization instead of full one. And then everything else in here is either matrix multiplication or matrix vector multiplication, or if you're solving systems like these right here, use backslash.
Okay.
Yeah, so in this case, the focus is not on an ordinary AX equals B problem. Like, I mean, that's what you worked on in chapter 3 homework. And I think we've beaten that horse to death. So I know that you know how to write code to solve AX equals B. In this problem, I'm fine if you're using backslash for that purpose.
Okay.
Yeah.
Thank you.
I have a question. Like, on say span. So, for instance, you say the range of A is the span of the first R vectors, left singular vectors.
Yep.
So I take span to mean the set of all linear combinations, right?
Yes.
So if I want to write that, can I write that as, say, using arbitrary constant?
Okay.
So if I don't want to write, say, range of A equals span U1 to UR, can I say sigma alpha 1 UR, where alpha are arbitrary constants?
Oh, I see. Okay, so this is for describing what exactly? This is describing range?
Yeah, so for instance, I want to write a range of this. So instead of writing span this, and I use sigma notation. So sigma alpha I UI, I runs from 1 to R. Is it the same thing as the span of this?
Alpha. Oh, yes, it is.
Okay.
Yeah, because you said they're arbitrary constants.
Yeah.
Yeah.
Okay.
Yeah, really, yeah. For describing it, this is any expression that represents arbitrary linear combination of these vectors. If you're trying to describe a range.
So this next question is not a homework question. So the house order reflections.
Okay.
Yeah. I don't know if there's a problem with the algorithm in the textbook.
Okay. So householder QR.
Yes.
Okay.
Yeah.
Oh.
So this 1 to M and J to M.
I think. Hold on a second. I'm gonna flip to my site here. I should mention here on my website on the page for the book there is a list of all known mistakes.
Okay.
There is a mistake in this algorithm.
Okay.
And I think I caught this when I presented it in class, but it's not okay. Yeah, like here. Okay. Oh, this should be 1 to m, like it is over here.
Okay.
And yeah, here and here.
Okay. Let me just quickly see if that works. Okay, yeah, I think I got it now.
Okay, good. Yeah, the last time I taught this class was in spring of 2019. The book had just come out in very late 2018, so I started using it right away for this class. And I think this is one of the first mistakes that was uncovered, and like, oh, it's all downhill from here. Okay. So if I ever get to do a new edition, it'll definitely be a lot cleaner. Have any other homework or quasi homework questions?
I have a question.
Yep.
On 4.1, it says we're supposed to do 3, 4, and 7, but 7 has to use the result for 4.1.5. Does that mean we need to also do number 5?
Okay. You do not need to prove number 5. You can take its results for granted. So you can just assume that the eigenvalue of a square is a square of the eigenvalue, and similar for reciprocal. You don't have to show why that's true.
Okay.
Yeah.
So you're just assuming it's true just for number 7.
Yep.
Okay. Thank you.
And yep. And since number 7 says use result of this, this explanatory text is also important for number 7. Okay, we still have 3 minutes. Any other? Okay, so that other least squares of linear constraints method will be included in the notes that I post. So I will see some of you in PDEs in a bit.